Okay, so now we are going to discuss the section 1.5, Griffiths' book on quantum mechanics, third edition. The title of this section is Momentum, but you will see that there is much more than just momentum here. A very important section. The concepts and the equations that you will see here will be using throughout this course. Okay, well, let's review something that we discussed in the beginning of these lectures. Now we said that all information about the system is contained in the wave function, right? So if we are trying to describe a particle, the absolute value square of this wave function at a certain time tells us, the probability for finding the particle here or there, right? So this is all that we know. We will only know exactly where the particle is if we measure it, if we measure its position. Before the measurement, that's what we have, this distribution of this probability. Once we measure, then it will take a stand. Once we measure, we will get a specific result. For example, we'll find that the particle is at position A. So in this case, we have the collapse of the wave function now to this position A. Now, if we repeat the same experiment, same initial condition, same initial wave function, let it evolve, everything is the same, so that at time t, we are back to this wave function here. Again, this is the distribution. We will only know the particle once we measure. So if I repeat this measurement, what we'll get now, we don't know beforehand. We may get A, or we may get a different position, who knows, position B here. Okay, and if we repeat the same story, same time, same, everything is identical, and we measure again the position of the particle, it can collapse. The wave function can collapse to a different position, let's say C. Okay, so we cannot predict the exact position and what is going to come out of this measurement. We only can have information about the mean value. We can repeat this experiment many, many, many times, and we will be able to get the mean value, okay, the average or expectation value. So what we are going to discuss here is how to obtain this mean value. Now, what is the mathematical procedure for that? Experimentally, that's what we do. We collapse the wave function. We go there, measure, and see exactly where the particle is. But mathematically, how this is done? Well, how do we compute this mean value, this expectation value? As usual, this is a continuous variable, so we are going to deal with an integral. We put here the variable and the probability associated with it, probability density associated with it. And this is how we compute this expectation value. That's the only information that we can get about the system, okay? Okay, so this is the story about the mean value of position when we are giving wave function in position. That's the way to get the mean value. How about get information about the velocity of this particle? Same story. We do not know exactly what is the velocity of this particle. The only information that we can get is mean value. Okay, expectation value. And how do we get that? Well, the derivative of that expectation value of x. That expectation value of x that we computed here depends on time. Because the wave function depends on time. The wave function depends on time, so this also depends on time. And so if I do the derivative of this expectation value, I'll get the expectation value for velocity. And now I want to show to you how we compute this expectation value. It's not as simple. And there is some interesting things that will come up here. So I'm going to copy that equation that we have above. So we have this total derivative. And here we have x and the probability density. Okay, similar to what we did in section 1.4. If you don't remember 1.4 very well, it's good to watch it again, to read it again in the book, because we are going to be using the same tricks. So I'm going to go faster now. Okay, so what we are going to do is we are going to put this total derivative inside the integral, and will become now a partial derivative, right? Because the function depends on x and time. So it becomes a partial derivative, and what we now have is x, this partial derivative, this absolute value square is the complex conjugate and the function, okay? So you see that this is becoming very similar to what we did in section 1.4. We also had exactly the same thing here. You may ask, oh, how about the derivative of x? X here is just a variable. It's not a function of time, so we do not do this derivative. Okay, so we just do the derivative of the wave function, which depends on x and time. Okay, this integral is from minus infinity to infinity, so let's put this here. What is it that we are going to do next? Well, so this term here involves the first derivative in time of psi and the first derivative in time of the complex conjugate of psi. Okay, what we do here, we substitute this part and this part using Schrödinger equation. That's what we did in the equation in section 1.4. When we do that, because the potential energy is real, we're only considering here conservative systems, because it's real, we see that the part of Schrödinger's equation involving the potential cancel. And then we do a trick, because once we use Schrödinger's equation, we get second order derivatives of psi in x, where we do a trick with this derivative, go back to equation, to section 1.4, and we find out that we can then rewrite this integral with these constants. These constants are coming from Schrödinger's equation. The x is there, and now that those derivatives will become derivatives now in x. Okay. So this is something that we already did in section 1.4. Let's see how we are going to go from here. Okay, so go back there if you don't remember this very well. Okay, so what are we going to do now? Well, look, what we have in this integral is basically something like this. It's a function of x with the derivative of a function of g, basically. Well, it's partial derivative, but that's what we have. Where, in our case, this function is x, and this derivative is that ddx of the whole thing. Well, how can we solve an integral like that? We can do it by parts, right? What is the solution? When we do it by parts, what do we get? We have f and g, and the borders here, the range of the integration. And then we have minus, and now we invert the derivative, right? So this becomes df in dx and g. All right. So this is the usual way to do partial derivative. If you don't remember where this comes from, it's worth talking about the parentheses. Okay, so suppose we have these two functions, f and g. And suppose we do this derivative in x. Well, we know that this will become f derivative in g plus derivative in f and g. Very good. Suppose we then do an integral in dx, integral in dx, integral in dx. Well, the first term here, integral of a derivative, gives us just fx. And then we have f g, derivative of g plus derivative of f and g. Okay, here with the extremes that we have here, it's from a to b, let's say from a to b. So here we have from a to b, a to b, a to b. Okay, so you see, this this integral here is this integral here, right? So this integral here, if I isolate this integral here as we have there, we have this first term, which is this. And this second term will become negative when we pass to the other side. Okay, so this is just a quick review of integration by parts, but what we are going to use is this into that integral above. Okay, so let me erase all this to get space. And let's now solve that integral. Use integration by part. So use integration by part, we have that constant, and then the function f and g, right? So it's the function f is x, and this is playing the role of g. So we have x and that whole term inside the parentheses. And this from minus infinity to infinity. Huh? Then we have minus the integral. Now the derivative of f is the derivative of our x, which is 1. Okay, so here we have the derivative of x, which is just 1, and our g, which is this whole thing. Okay, all that. Now, this first term, we are looking at minus infinity and infinity. So we are looking at the wave function, the derivative of the wave function, minus infinity and infinity. We said that for the function to be square integral, for the function to have physical meaning, this has to be 0. No, the functions that we are interested will satisfy that. So the only thing that will survive in this story is this minus, because there is a minus sign here, minus that constant and the integral of these two terms. Okay, this from minus infinity to infinity. Okay, let me do one more trick in this story, which is these two terms, they are very similar. So what I'm going to do is I'm going to do another integration by parts just for this side. And so doing another integration by parts just for this side, what we are going to get, so we get, if we do a partial integral here, we'll have, so let me isolate it just this part. So what we are trying to do is this by parts. So we'll have this in its range from minus infinity to infinity minus, now we invert the derivatives. We have this and this one. So why this is interesting? Because you see, this term here is now equal to this one. This, we have a minus sign. With this minus sign, we get plus. So we have this term here twice. And how about this other term? This one is 0, as we said. The wave function at minus infinity or at plus infinity has to go to 0 to guarantee that we can normalize. So if we come back to our integral, we now have minus I h, there is twice the same term, which is this one, dx, from minus infinity to infinity. So let's rearrange things a little better. These two cancels, and then we can rewrite this expectation value of the velocity as wave function. Now this minus I here, I'm going to put it in the denominator. So it becomes I positive I m. Here we have this derivative of psi. Okay. Well, this is the expectation value of velocity. If we want the expectation value of momentum, which is we need multiply the velocity by the mass, right? We then get this other expression. The m cancels and we have this. So you see that the way to compute the expectation value of momentum is a little more involved than the way to compute the expectation value for position, right? How did we write the expectation value for position? We wrote it like this. But in fact, we can also write this is equivalent. We can write it like this. The complex conjugate x, the function, and then dx. So now we put it in a form very similar to the way that we are computing the expectation value for momentum. What is this form? We make a sandwich. Okay, so this is the real expression. We make a sandwich, whatever quantity, so I'll put it, whatever expectation value we are trying to compute, the way to go is to make a sandwich between the two wave functions. We put this quantity that we are trying to compute. Now, this quantity that we are trying to compute is what we called in this mathematical formalism to obtain the expectation value. This thing that we put in the middle, sometimes we even put a hat here to denote, to say that this is an operator. Okay, so the operator position, when it sees a wave function in position, it just becomes the variable. So that's why I can move this x around because it's just a variable. But the operator momentum, when it acts on a function of position, it becomes that derivative above. Okay, so it's something a little new for you, but the way that we compute expectation values in quantum mechanics is using this idea, the sandwich um, uh, between the complex conjugate of the wave function, putting in between the complex conjugate of the wave function and the wave function, the operator that corresponds to the quantity that we are trying to obtain. Okay, so repeating, what is physical? What can we get in a lab when we are making measurements of quantum systems? We can get expectation values. Okay, we'll repeat the measure many, many times, do an average of each value that we get, and we then obtain expectation values. Now, so the formalism of quantum mechanics allows us to obtain these expectation values using the wave function. Okay, we do not know exactly what is the particle, what is the position, what is the momentum before measuring, but using this probability distribution, we can get the mean values. How do we compute these mean values? You put the integral, sandwich the operator of the quantity between the wave function. So this, very often people put this hat to remind us that we are talking about operators. So what is an operator? Is a way to act on the function. The operator momentum acts on the function. How? With a derivative. The operator momentum, so the operator position acts on the function. How? Just giving us the variable. Any other quantity will follow the same procedure, the sandwich. So for example, if we want to compute the expectation value of kinetic energy, what are we going to do? Well, kinetic energy is momentum square over 2m. That's what you learned there in classical mechanics. Now we are talking, we need operators. Okay, so the operator kinetic energy is what we'll have to put here now, sandwich, to get the expectation value of this kinetic energy. Okay, and what is this operator? Well, the operator momentum is h bar over I and the derivative. So the operator, I'll put the hat there, the operator kinetic energy, when it sees the wave function in position in x, it becomes h bar squared minus 1 because of this I here. And then we have 1 over 2m second order derivative. Okay, so if you want to compute the expectation value of kinetic energy, how are you going to do that? Like this, minus h bar squared over 2m second order derivative on that side of x. Okay, so any general quantity that you want to compute the expectation value that depends on x and p, how are you going to do that? You put it in the sandwich, okay? And wherever x appears, it will become the variable x. Wherever p, the momentum p appears, it becomes this derivative, okay? Acting on this, on this wave function. Okay, so this is the way to obtain expectation values of quantities in quantum mechanics. Very important. We'll be doing this all over this course. There is a problem that I suggest that you try to solve. There is a video about it, problem 1.7, where we calculate the derivative of the expectation value of momentum. So this is a good problem to solve because it connects with a very important theorem in quantum mechanics, which is known as the Ehrenfest theorem. So please solve this problem. If you have any difficulties, there is a video available for it.